Good day and welcome to Big Bad Tech. I'm instructor Jim Pytel, and today's topic of discussion is synchronous generators. Our objective is to examine electrically excited synchronous generators on an introductory basis. We'll explore those mechanical and electrical properties that influence resultant electrical power output. This lecture is limited in scope to synchronous generators in unloaded, isolated conditions and does not discuss how generators react to different load conditions nor generator synchronization. We'll explore loaded synchronous generators and generator synchronization in greater detail in later lectures. This lecture operates under the presumption that viewers watch the electrically excited synchronous motors and synchronous condensers lectures, both available at the Big Bad Tech channel. Additionally, this lecture operates under the presumption that viewers have some level of familiarity with squirrel cage induction motors and asynchronous or induction generators. We'll use this prior understanding as a basis of comparison for today's discussion about electrically excited synchronous generators. If you haven't watched these lectures yet or only dimly recall their contents, please bring yourself up to speed and return when you are so qualified. In the aforementioned lectures on asynchronous or induction generators, we'll learn that asynchronous generators necessitate connection to a previously established three-phase AC system. As we learned, a portion of the power an asynchronous generator necessarily draws for operation is directed towards a reactive interchange and goes towards establishing the rotating magnetic field in the stator. This implies asynchronous generators continually consume reactive power, even when exporting real electrical power for use. In summary, it takes power to make power. Additionally, an external prime mover must turn an asynchronous generator rotor faster than the synchronous speed of the stator for induction to take place. Synchronous generators, the topic of today's discussion, in contrast, can operate without an external three-phase AC power source and are black start capable, meaning from utter darkness, i.e. a grid in a completely depowered state, they can begin generation even if in isolation. For this reason, a vast majority of large mission-critical generators like hydropower dams and coal-fired power plants are synchronous generators. Additionally, synchronous generators, given proper control mechanisms, can operate at unity power factor, i.e. neither supply nor consume reactive power. Finally, an external prime mover must turn the rotor of a synchronous generator at synchronous speed. Again, the primary distinctions between asynchronous or induction generators and synchronous generators, the topic of today's discussion, are as follows. Asynchronous generators necessitate connection to an existing three-phase AC power grid. Synchronous generators, in contrast, can exist in isolation and are black start capable. Asynchronous generators must continually consume reactive power to power the induction process central to their operation. Synchronous generators, in contrast, can operate at unity power factor given proper control mechanisms. And finally, the rotors of asynchronous generators must turn faster than the synchronous speed of the stator, whereas the rotors of synchronous generators must turn at synchronous speed. Lastly, to make one more subjective distinction between these styles of generators, I should also mention that induction-style generators have a general tendency to be large in number but small in size, principally because they are relatively inexpensive and simple to operate, whereas synchronous generators are few in number but large in size, principally because they are somewhat more costly and complicated to operate. There are obvious exceptions to these sweeping generalities. Let us briefly review the parts of a synchronous machine. As you are no doubt aware, an electrically excited synchronous machine consists of three electrically isolated windings in the stator in a Y or a delta configuration and a DC field winding on the rotor. The rotor field winding is accessible via a set of slip rings which maintain electrical connection regardless of rotational position to a stationary DC source known as an exciter. In motor mode, three-phase AC is supplied to the stator windings, which create a rotating magnetic field. The rotor is then energized by DC electricity, which establishes an electromagnet. The electromagnet on the rotor locks into the stator rotating magnetic field and follows it around and around and around. As long as the load torque remains under the pullout torque for that particular level of DC excitation in the rotor will maintain synchronous speed and stay locked in step with the rotating magnetic field on the stator. In summary, while in motor mode, the stator consumes AC electrical power. The rotor consumes DC electrical power. This incoming electrical power is converted into mechanical power in the form of rotational speed and torque. The other aspect of synchronous machines, generator mode, is slightly different. In generator mode, the rotor is energized by DC electricity, which establishes an electromagnet. Then some outside force known as a prime mover, either falling water, moving wind, expanding steam, or an internal combustion engine, turns the rotor inside the stator. As the electromagnet on the rotor passes in close proximity to the stator windings, a voltage is induced across the stator windings. In summary, while in generator mode, the mechanical power of the prime mover and the DC electrical power consumed by the rotor is converted into AC electrical power output on the stator. The simplification of the generation process implies a certain dependency between the mechanical and electrical properties and the physical construction of the synchronous generator and the resultant AC electrical power output. The goal in today's lecture is to determine which input properties influence which outputs and demonstrate how one goes about establishing electrical output with the specified parameters. Of primary concern regarding the desired electrical output are four important properties: phase sequence, phase shift, frequency, and voltage magnitude. Let's deal with phase sequence first, since it's probably the most intuitive of these properties. Rotational direction of the prime mover influences which winding experiences peak voltage in relation to its peers. Using this simplified diagram, when rotated in a counterclockwise direction, first winding 1 experiences peak voltage, then 2, then 3. In contrast, when rotated in a clockwise direction, first winding 3 experiences peak voltage, then 2, then 1. In summary, rotational direction of the prime mover determines phase sequence. Phase shift, in contrast, has to do with the number and the physical placement of the windings on the stator. Using the simplified diagram with 3 windings, each with a relative 120-degree physical offset, each winding experiences peak voltage at a relative 120-degree electrical offset. This is a common arrangement for industrial 3-phase AC throughout the world, albeit not the only means of making multi-phase AC. For example, consider a 4-phase AC system with 4 windings at 90-degree offsets, or a 5-phase AC system with 72-degree offsets, and so on. In summary, the physical construction of the stator windings influences the degree of phase shift between the related phases. Let's now take a look at frequency and voltage magnitude. Frequency would measure how many cycles of voltage waveform it experiences per second, measured in units of hertz, where 1 hertz is 1 cycle per second. A related property, period, is the length of a single cycle. Period is the inverse of frequency, and frequency is the inverse of period. It stands to conjecture that the faster the rotor electromagnet turns inside the stator, the more frequently each stator winding experiences a full cycle of voltage, thus resulting in higher frequency output. In contrast, the slower the prime mover drives the rotor electromagnet inside the stator, the less frequently each stator winding experiences a full cycle of voltage, thus resulting in lower frequency output. Long story short, the rotational speed of the prime mover directly influences output frequency. Thus far, we've discussed phase sequence, phase shift, and frequency, so we're left with one electrical property: voltage magnitude. What controls voltage magnitude? Interestingly, voltage magnitude is not dependent upon one generator input property, but rather 2. First, voltage magnitude is directly proportional to DC field current, which kind of makes sense. More DC field current results in a stronger rotor electromagnet, thus more voltage induced on the stator coils. Second, voltage magnitude is also dependent upon rotational speed, which again kind of makes sense, given the process of induction, which states a voltage will be induced across the terminals of a conductive coil proportional to the rate of change of magnetism and the number of coils in the changing magnetic field. Note the dramatic emphasis on the phrase rate of change. The faster the external prime mover turns the rotor, the more voltage will be induced across the stator windings. This is to suggest that not only is voltage magnitude dependent upon 2 input properties, but also rotational speed of the prime mover influences not 1, but 2 resultant electrical output properties: frequency and voltage magnitude. This can present a challenge when establishing electrical output with the desired phase sequence, phase shift, frequency, and magnitude. Follow this example. Consider a rotor spinning at a certain speed in a given rotational direction inside a stator with a specified arrangement of coils with a certain level of field current. The resultant 3-phase AC electrical output will have a specified phase sequence, phase shift, frequency, and voltage magnitude. If we kept everything the same, i.e. the same rotational direction, inside the same stator, with the same field excitation current, however, stepped up the rotational speed, not only would frequency increase, but also voltage magnitude. Again, if we kept everything the same, i.e. the same rotational direction inside the same stator with the same field excitation current, however step down the rotational speed, not only would frequency decrease, but also voltage magnitude. This presents us with a challenge. Let's say you had a phase sequence, phase shift and voltage magnitude right, but your frequency was too slow. If you stepped up rotational speed to the proper frequency, you'd also increase voltage magnitude, potentially overshooting your desired specification. This begs the question, how the hell do you set up a generator such that it delivers a desired phase sequence, phase shift, frequency, and magnitude if one input, rotational speed, influences two properties, frequency and voltage magnitude? The answer is, establish desired phase shift, phase sequence, and frequency first, and don't worry about voltage magnitude until the very last step. Oftentimes, a generating facility will first install a stator with a desired number and physical offset between stator windings to ensure proper phase shift. Next, they get a prime mover rotating in a particular direction to establish a desired phase sequence. Then they ramp up prime mover speed until frequency stabilizes at the desired specification, and then, only as a final step, ramp up field current excitation until voltage magnitude reaches the chosen value. Establishing a phase shift, phase sequence, and frequency first thereby allows an operator to vary field excitation current and field excitation current only to achieve the desired voltage magnitude specification. If you went about this in any other sequence, you find yourself fumbling to achieve voltage magnitude at the expense of frequency, and vice versa.